In this video, I'm going to walk through how to use the water quality portal. There's a few different ways of getting data we need for this class, and I'm just going to walk through one, kind of come up with an example on the fly, and then look at how to build that into a report. So we come to the water quality portal. There's a good how-to and user guides. Some kind of other things we can explore. And this water quality portal uses data from both USGS, EPA, and the National Water Quality Monitoring Council. So there's a bunch of data in here, including data collected by states, federal entities, tribes, and local agencies. And so most tribes have EPA grants to monitor water quality on their lands, and they're required to upload those data to EPA. So we can use this portal to find those data as well. So let's just, excuse me, start here. And this is a pretty interesting database because there's data from all around the world. Let's go down to America here. And so we've got NWIS, which is USGS, sorted, which is EPA, steward, which I don't recall what that is off the top of my head. Let's say we just want to go to Washington. So there's a couple of ways of doing this. One is to think about your parameter nationally. For the purposes of the project, I would really encourage you to think as geographically specific as possible, because that will allow you to build a better report. Meaning, if we look at glyphosate nationally, there's some trends, but if you can look at it maybe in an area that has a lot of soybean or corn that use a lot of glyphosate, that would make more sense, right? You can make a mechanistic link between the parameter and land actions happening around there. For this example, I'm going to use Whatcom County. And so this gives us country, state, county. Now there's all these different site parameters, site IDs, a whole bunch of things we can look at. Now let's just see, what are we looking at here? So if we click show on map, we see we've got 2,682 NWIS sites. So those are USGS sites. And for sorted, 2003, those are EPA sites. So we hit continue. And this isn't required to look for the parameters. It's just, to me, interesting to say, okay, where is the most data in Whatcom County? Come on. So here's, Whatcom County. You can see we've got a lot of data here. And it's kind of interesting. It tracks up the rivers, which makes sense. So the NWIS data is USGS. So we're looking at things like stream temperature, stream flow, turbidity, other parameters as well. So we have a pretty data-rich area. You can click on any one of these and add it to the sites and download the data for that specific site. So if there's a specific location you're interested in, what are they doing out here? You could download all of these data. Now, let's think of a parameter. Now, one parameter that's really important in drinking water and groundwater in Whatcom County is arsenic. We tend to have a lot of arsenic in Whatcom County. And so this is an example of a parameter where we could tie it into our local geology. You could tie it into land use. If arsenic is detected in a well and you're trying to build a house, you have to put in either a deionizer or reverse osmosis or some form of water quality treatment at your house if you want to build on your land. And so it's a really common thing in Whatcom County. It's really common on Lummi Island as well to have high arsenic. And so there's a number of systems that you can put in either for small developments, like 20 or 30 houses that share a common well, they'll treat that water. Additionally, if you're a single house, there's options you can do to treat that water. So here's, kind of a storyline, right? Whatcom County, geology, naturally occurring contaminant. It has a legal limit. A lot of our water is above that legal limit, and so we require filtration. You can examine those filtration systems, kind of the cost, and build out a pretty good, 15-page report on that. So how do we get to arsenic from here? Well, one is to look at the parameter code. Now this says NWIS only, so this is only USGS data, but we need a parameter code. What's the parameter code for arsenic? Well, I don't know, so let's click on the question mark, and it'll bring us to this website. Now we can scroll through and look at a bunch of different type of parameters, or we can enter arsenic. Look, I've already done it, and hit submit. Now, apparently there's more than one type of arsenic. Look at all of these types of arsenic. So what we're really, one, it's kind of hard to say, like, which one do we care about? Well, if we're looking at drinking water, all these bed sediments, soils, not relevant. Arsenic water, that's relevant. Unfiltered, we probably want filtered. So most sampling is based on filtered. Now we can run multiple parameters as well. And so one way to do that is to say, maybe look at unfiltered, filtered, and maybe unfiltered micrograms per liter. Like you can add 3 or 4 in, and then see where there's the most data, and then base your analysis off that. Or if we're interested in arsenic impacts in aquatic systems, maybe water's not what we care about most. Maybe it's bed sediment or soil. So there's different, it kind of depends on where you want to go through report. For the purposes of this examination, I'm going to use water filtered micrograms per liter. So that's 0, 1,000. So I'm going to copy that, bring it over to our data portal, paste that in, and then we can also show sites on map again. So this is just a way of visualizing the data, which I think is pretty interesting. So again, we're just NWIS sites. Now we're down to 53. So we had 4,000 before. So now we see some USGS data. One here from right near Whatcom Creek, a lot along the Nooksack Delta, Sumas River, a few more up here. So this is, oh, there's a bunch up here too. Look at that. So we've got some sample data. Now, oops. Now when we want to download, there's a bunch of different ways to download. You can do comma or tab separated. This does give you the option to download them in Excel, so I would just do that. I'm going to start with site data only, and download that first, because this will give us the metadata for where these sites are. So I'm going to hit download. It's going to think for a second, and it's going to think for 2 seconds. Okay, so 53 sites, continue, and that's going to download to a zip file, which is in my downloads folder. So open that, and then it opens a station file. Let me bring this into the screencast-o-matic size here. Nope, it's fighting me. Give me 1 second. And bring the lower side up. Come on. Come on. There we go. So this is those 53 sites. It tells us who did the monitoring. The location identifier says like the site code, basically. The general location name, stream or well. This will become important because wells are Are things people drink out of? Streams? Perhaps not. Drainage area, if applicable. The GPS location, which is nice. The Latin long. The what's that called? That's not baseline. It's the GIS people will know off the top of their head. Datum. And vertical measurement, and then a bit about the aquifer type. That's pretty interesting. What water basin they're in, formation type. Huh, cool. Well depth. That's interesting. So maybe if there's a relationship between well depth and arsenic, that would be interesting. So like that's a deep well. Many of these are shallow. Look at this, in the 20s, 30s, 18 feet. What? 47. Let's see what 47 is. I selected it, so it shows up here. Yeah, so this could be like an ag. It says ag 13. I don't know if that's a agricultural well. That's interesting. And we can look up exactly where that is too. Wow, that's a shallow well. Okay, so we'll save this because this is our metadata. So if the later data just has site codes, we can bring that back to here and say, okay, that data is from a well. You can plot exactly where that was at, and you can tell us how deep it is. And so we'll have to keep track of a lot of different data here. And so data management is going to be really important. So if it were me, I would, save this as something different. My final code report station, something like Whatcom arsenic. So I can come back and find it. And now let's get to the actual data, right? So here, I believe we want project data. Let's try that. Nope. Okay, sample results. There's a bunch of different stuff here, and again, this is one of those things where it's going to take some exploration on your point. So now we have 119 samples. So go back to our downloads file and open the results. And again, it's opening too large. Okay, so now the same thing, organization, activity identifier, routine sampling, surface water. We've got the dates. Somebody's go back, look at 65, 67, interesting. Routine sampling. Okay, let me just do something real quick here. Oh, here's our location identifier. Okay, that's what I was looking for. So let's see if we use. Yeah, so that right there comes from here. So there's some matching that'll have to happen. You can sort this by site, which might be worth it to see where we've got the most amount of data. To do that, I would go data, sort. Why is it giving me by column? I don't want that. Let's try it again. Expand. Huh. It should give me the actual name of the header, not the location identifier, but we want V, sort A to Z, that's fine. So now we've got this sorted by location identifier. So now we can say there's 8 points of data there, 14 here. This will allow us to scroll around to see where we've got the most amount of data. Cool, so now we're organized by site, and we can scroll over and look at our actual data. So arsenic dissolved, zeros, so 1, 10, some more zeros, and some values here that kind of vary. Six is a big number. Let's see what's going on there. 1990. Huh. And then lots that are sub 1. Cool. Well, what does that mean? This is submersible gear pump. This is probably a well. Same here too. Interesting. Okay. So what does all this mean? What's this last one? GPS code. Historical. Okay. Cool. So now we've got these data. We can just kind of look at these data here. We're kind of between 0.08 and 0.2. Great. What does that mean? So let's go back to our website and we say, okay, arsenic water quality criteria. Like, what is a good arsenic value? What's a bad arsenic value? And there's different criteria. Some are for aquatic systems and some are for drinking water. I believe the one I was looking at was this one. National Organization for Water Quality Criteria, Human Health Criteria Table. Now there's two different things here. There's human health for the consumption of water plus organism, human health for the consumption of organism only. So this means if a fish is swimming around in this water, the value would have to be below 90 for it to be safe. If you want to drink it, it has to be below 70. It's a big difference here. So what this is doing is thinking about water in two different frames. One is drinking it directly, and the other one is eating fish that comes out of that. So we can either scroll down to arsenic, or we can Control F, find arsenic here. And so here's our two data points. So for drinking water, it needs to be below 0.018, and for aquatic life, it needs to be below 0.14. These data, we can go and verify again, are in micrograms per liter. That's going to be really important to make sure your data are in the same units. And if we go back here, micrograms per liter. So we can compare that here and say, well, most of these are above the recommended value for drinking water, which was, let's go back to that again. I already forgot. 0.018. 0.018. Many of these are above the zeros, are not, obviously. So fairly high amounts of arsenic. Now we'll have to go back and tie that into what these sites are. Is it stream water? Is it individual wells? But this alone gives us a fair amount to get started on. From here, what I would do is I would save this as the data Whatcom County, and then I would use I'll use the right word here, the parameter code. Yeah, I would save it by the parameter code, which the parameter code we used was 1000. And I'd go back and I'd play with a couple of the other parameter codes to see if there's more data. And so we had, let's see, I'm kind of curious about this one. And then we can kind of start to compare to see where we've got different amounts of data. let's just throw that one in there. Sample data. Again, we'll need the station data. There's only 65 there. That's not a lot. Spin segment, filtered. You can see what this one is. But I just kind of keep poking around and figure out which one's got the most data, and then figure out what that means as far as sampling. Yeah, I didn't think that was a very used one. I'm kind of curious by bed sediments, but see here, this is the thing where it's like it can be bed sediment in a variety of different ways. There's suspended sediments. I wonder what that's like. I'm just copying and pasting these. Oops. No data here. So, but with just the first one we picked, there's a fair amount of data there to compare to drinking water standard. And so from here, what I would do is be sure to catalog the station information, the results, maybe even put them in the same folder, so we can go back, pull out the data we want to look at, compare that to the station, and then plot those. There's a couple different ways we can think about plotting the data, and we'll spend a bit of time on that. But here we've got numerical values. We have dates as well. So like the first thing might be, well, maybe I want to present it against time, and some of these go way back. Look at the 60s. So for these stations where we have a lot of good data, yeah, like this station looks really good here. Those were taken between 2012 and 02. I would think about really plotting these against the EPA guidelines, because depending on what type of data we find, you might not have a really strong time series. So plotting the data versus time might not be the most important. We could also think about it as number of samples above the regulatory limit. A number of samples below would be another way of quantifying these data. Averages, standard deviations, maybe be important if it's also qualified with number of samples above threshold, because you could have an average and a standard deviation that's well below the threshold, but if you're still getting hits, still getting samples that are above that threshold, that's going to be really important to record as well. So I would start. There's a couple of ways to think about it. One is like to start spatially, like if you care about Whatcom County or Yakima County or wherever, kind of start there and poke around and just see what's out there. And the other way is to maybe start with the contaminant. We could actually go back to the water quality. We could actually go back here, delete Whatcom County, and do all, and go back to our 0, 1000. Show sites on the map. Oh, there's a whole bunch on Fidalgo Island by Anacortes. That's interesting. And see, okay, where is the most amount of arsenic data collected? There's a bunch over here. So that would be one way of thinking about it. Or go based on site. So it's pretty interesting. So from here we could do the same thing. We could download all these data. We have to download the site data first, so we know what we're working with. But we can download all the data now. Get 6,000 data points. Let's do this. This will be kind of an experiment here of how to deal with 6,000 points of data. We'll see how Excel likes it. So let's go back to our downloads. So done downloading. There it goes. Okay. Okay, and then we want to sort these again. By V, which is, sort these again by V, which is monitoring location. And then what's our actual data? It'll be interesting to sort by data results. We've got, come on, open up. Results measured value. Oh, results unit. Okay, so AH is measured value. So let's try sorting by, oh, my list has headers. And then why, there it goes. My little buttons aren't showing up here. Then by, we wanted, second here, second, let me come back over here. Results measured value, okay. Sort, my data has headers, monitoring locations, plus measured, result measured value. A to Z is highest to lowest, okay. Separately, oh, I see, okay. So monitoring locations, and then the values with this, within those locations. So this would be a good way to just look over the state and see where we have the most data and go from there. This one's looking pretty good. And then we can go back and see what station that is. You can even just Google that station ID and it'll give you, there's a lot there, yeah. It'll give you information on that station. This one's got a bunch of data. Around here, there's lots of zeros. 1s and 2s. Big values, holy cow. 20s, 10s. I'm a little suspect because these are like round numbers and like it's unlikely that they measured 10.0. Maybe that's an old measurement. 65, yeah. So I think analytical methods have improved in the past 80 years. Yeah, so those 10s make me cautious. 1s and 0s. Let's see how old these are. 80s. So there's a fair amount. I like these data a little bit more that have more significant figures. Something from the last decade. We can sort by time as well, and then look for more recent data. But there are, sorry, you're probably getting dizzy here looking at all this. There are, what was it, 6,500 samples here, a fair amount. So, sorry, just close your eyes. I'm gonna skim really quick. So to me, like the agricultural, I know Yakima has some, these are huge numbers here. Those are all from the same station and fairly recent. So something interesting is happening here. So from here, I would think, okay, something's going on at this station. And there's a lot of data for this station. So I might pull that one and see what's going on here. And again, it's going to be very iterative. You're not going to just get your answer in 10 seconds. Wow, look at all that. There's a lot of data for that station. But here we've been able to basically go from, there's a parameter I'm interested in to something's going on with that parameter at this site. And so we could easily pull that site up and then start to build a report around that as well. For something like arsenic, I would argue that you probably want multiple stations, right? But you're going to have to think about your parameter and look at it from different angles to figure out where to get the best data. And if you find a parameter and you can't really find much on it, maybe think about a different parameter. Your life is going to be the easiest for whatever parameter has the most amount of data. That's ideally spatially constrained, again, so we can draw those mechanistic links between land use practices, natural geology, and those parameters as they relate to either aquatic or human health. So in short, we have a couple different databases we're going to look at in this class. This is one of them. I think it's quite powerful. It does take some time to get into, and there's again a bunch of different types of data we can look at. We could look at PCBs in Whatcom County. Apparently there's no data. So, it's going to be a lot of poking around. So what about nutrient? I'm sure there will be organopesticides. Okay, that's interesting. See what's the sediment toxicity? Oh wait. Oh, I can add multiple. That's cool. And no data. Let's take off Whatcom County. See if that helps. Nope. So some of these aren't going to be for everywhere. Let's try inorganics, major, and non-metal. That should give us something. Really? Okay, well, maybe that one's kind of a bust. Microbiology not assigned. Nutrient, come on. Okay, so something's funky in the way that that's coded. Because come on, Hatch. My parameter code was in there. There we go. It was searching for only nutrient data with that parameter code in it. There we go. Now we're cooking. Now things are better. I really interested in PCBs. Okay, let's try that again. Now that I realized that I've had a parameter code in there, I didn't need it anymore. There we go. So now we're searching for EPA sites and USGS sites, so that's going to open up more data. Interesting. Okay, so let's, ooh, that was a lot of data. Sorry, I closed it too quickly. 1,200 data points. The site is going slow. It's super windy out. I think it usually when it's windy, for some reason, wind impacts the internet due to some unknown covariate. Okay. Okay, so that's result 4. Come on. Okay. So again, we need to download the station data to figure out exactly where all these are, but this is cool because it's sediment biological tissue. So this would be one where you probably want to sort by sample type because you can't really compare sediment to water to biological tissue. But again, you got, 1,100 points of data here, so there's a ton. Dates, let's see what our data look like. characteristic name, PCPs, accepted drive, codes, result actual estimated. Okay, and here's our values. Wait, let me see, what's this? Detection, quantification limit, result laboratory. Yeah, very cool. Wow, fish tissue. So there's a ton here. So, sorry, I highlighted 150 here. Sediment, so that's a percentage. So we got sediment, and then tissue is the one below that. Nanograms per gram. Cool. A lot of data. This, it's got English sole, the genus and species name, rock sole carcass, rock sole, English sole. So tons of information. Whole fish, when was that collected? So this would be really interesting, 2004. So PCBs would be really interesting, particularly because they're in fish, because you could tie it back into the fish consumption rate, which is Oncorhynchus or salmon. Clarkii, that's cutthroat. Sorry, I'm getting distracted. Fish consumption rate is a move that the tribes are pushing to alter the way that EPA analyzes or determines the risk to human health based on how much fish people eat. And it used to be 6.8 grams per day, meaning the EPA assumed that people ate 6.8 grams of fish per day or less, which is roughly the size of a piece of fish, the size of your pinky nail. And many communities, native and other communities, eat much more fish than that. So they argue to EPA that the current regulatory regime does not adequately protect their human health, and argued for a fish consumption rate closer to, depending on which values you use, 300 to 68 grams per day, so a big change. And so that would matter for things like this, meaning, you can have a lot of toxins in fish if you only eat a little bit a day, but you can't have a lot of toxins in fish if you eat a whole bunch per day. It's pretty interesting. So here, like this might be a better example than the arsenic, because we went from really not knowing much to finding a whole bunch of data. So again, we download the site data so we can compare those. But that's really cool. So I bet a bunch of these aquatic ones from here. Okay, I'll stop rambling. I would, if I was thinking about parameters, this might be a good way to start, is open up this data set and just start seeing what's out there. So again, there's a couple different ways of thinking about this project. One is, I really care about place X because of I grew up there, whatever. Or I really care about this parameter. So if you care about a place, I would start like this. I would start with Whatcom County, and then just kind of going through these broad characteristic groups, and then maybe define that a bit more to certain parameters. Or if you care about the parameter, 20,000, wow. I would start with the parameter, look state or nationally, depending on what that parameter is, where it would make sense that they'd have the highest values or the most amount of data, and then work backwards from there. So I would expect a good chunk of time, and devote it early, a good chunk of time to really exploring these different data sets, databases. The TAs will be available to help you as you start hitting kind of brick walls and get stuck. That's what a lot of the lab time will be directed towards. So I encourage you to start early and really just sit down and start cruising through the data, catalog it, be sure to save it with file names so you can find it again, and start to build out a picture of what and where, and then build a narrative around it. So I hope that helps. Thanks for sticking through it.